vai estar na página do evento. Acho que vamos fazer em inglês, porque a gente não fala português.
Claro, claro.
Okay. It's a pleasure to start our seminars in probability in stochastic process. And for our first seminar, we have Daniel Ungaretti. Daniel worked a lot in percolation during the master and the PhD. He did his master in UFMG and his PhD in INPA. He did also a postdoc in Unicamp, right? And now he's starting a postdoc here in IMI at USP. And welcome, Daniel, to USP. And I would just ask you to turn off your microphones, and if you have questions, you can send by chat or wait up to the end of the seminar and ask them. Okay? So you can start, Daniel. Thank you. Okay.
Thank you, Aline, for the introduction. And also, thank you for receiving me so well. I am just starting at USP, and well, I know the times are a little bit troublesome, but I'm glad that I'm starting this new part of my research. And today, I prepared a little bit a talk to say to you about what I studied at Campinas with Serguei Popov. This is the part that I did is joint work with Serguei and also Leonardo Rolla. And today I'm going to talk about conditioned walks on the plane. So I divided this talk a little bit in two parts. Just check something here. Okay, you can see, right? Yeah, you can see. And okay, so at the first half, I will talk about random interlacements model and its connection with random walks on the torus. And afterwards, I will talk about how we can generalize, well, actually define the model at dimension 2, and also talk about properties of a random walk that is used defining the model on dimension 2. So, okay, before going to the second part, let's start defining our model. So we want to understand the trace of a random walk on a torus. So suppose you have a torus with side length n, okay? We are on dimension 3 or higher here. And you start a random walk. You begin at some point and you start walking until at some time you stop. And now what you want to do is to say something about the trace of the walk. Well, of course, it depends on how much you have walked, right? If you walked if you didn't walk for too long, then the trace will be very small compared to n. And also, if you walk for too long, then eventually you will cover all the torus. So there is some choice here, and considering that the volume of the torus is given by n to the d, a natural choice is to consider some proportion of the volume. So this is the number of steps that we are going to take. And then we have two sets, the vacant set and the covered set. The vacant set is simply the set that was not touched by the walk, and the covered set, it's complementary. And then we can ask questions about how much has been covered or not. And a nice question also is the vacant set disconnected? So here in this picture, for instance, if we were talking about Z2, you can see that this vacant part is disconnected from this one. But notice that this question is not so clear. It's not so clear when you are in dimension 3 or higher, because it's more difficult to enclose some region on using the random walk, okay? But I'm just calling attention to some of the details of the model. And so to understand this question, we need to understand the walk on the torus. So here we are considering, instead of simple random walk, a lazy random walk. And simply because it's easier for us to deal with a Markov chain that is actually irreducible and aperiodic. And so here is another representation of the trace. And what we want is essentially the following. We fix some finite set of ZD. And we want to understand the trace of the walk inside this fixed set as we make n tend to infinity. Okay? So let's recall some properties of the lazy walk. So the first natural property is that we have a stationary measure. It is precisely the uniform measure on the torus. Also, we have, of course, that we converge to this measure as we take a sufficient high number of steps. And moreover, we have a good control of the spectrum of this Markov chain. So since we have a lazy walk, all eigenvalues of the chain are positive, are non-negative. And also we have a good control of the spectral gap. You can prove that this is a bound for the spectral gap. And, well, why is this bound nice? Essentially because you can define, we have the notion of the relaxation time that is simply 1 over the spectral gap. And we know that the relaxation time is very related to the mixing time. Actually, there is some expression involving the logarithm of the minimum of the stationary measure here times the mixing, the relaxation time. Maybe this one, the one is swapped. But essentially, what's the mixing time? Just a brief recall. Well, you have some starting position for some starting distribution for your chain, and you know that you will converge to the stationary measure pi. So essentially, when you start from, for instance, a fixed point and you evolve the chain, you are far away from the stationary distribution, but then suddenly at some point you will get close to the distribution. And this approach happens essentially at the mixing time, and afterwards you will converge exponentially fast to the exponential distribution. This is simply the total variation distance between the initial distribution and the stationary distribution, okay, after you advanced it by n steps. So another useful quantity here is the regeneration time. And this is simply a little bit higher than the relaxation time. And why is this nice? Well, I've just said that if you wait until the relaxation time, you will be sufficiently close to the stationary measure. And then for the regeneration time, we have some explicit bounds for how close we are to the stationary measure, okay? So now let's talk about properties of simple random walk on the whole space. We know that for dimensions 3 and higher, simple random walk is transient, meaning that you cannot return to the same point infinite number of times. Eventually, you will escape to infinity. You can define a green function. What's the green function? Well, you can interpret it as the mean number of visits to the origin when you start your walk from a site X. And well, why is this function that I've just defined useful? Well, it is simple to prove using Markov property that this function is harmonic. And what do I mean by that? Suppose you have some site X, and you want to evaluate the value of the function at X. You can prove that this is the same thing as averaging over all neighbors of X the value of the function at each neighbor.
Daniel, can I, we have a question. Do you use time for the quantity because of its relation with mixing time, or does it have an independent time interpretation?
Sorry, what do we use time for this quantity? I didn't understand which quantity.
Quantity of relation time.
Ah, relaxation time.
Yeah.
My question is, why does it call relaxation time, since you're defining it to be something to do with the matrix? Why time is in this context? Is it only because it relates to the mixing time, or does it has another interpretation?
Yeah, it's just, well, you can define this quantity in a very using only linear algebra, and then you have essentially no interpretation using time. But essentially, since we can interpret this as roughly the time in which we are close to stationarity, then we just called it relaxation time. But maybe there is some deeper reason. I don't know. Maybe.
Okay, thanks.
Okay. And so just return to the line of reasoning here. We were talking about the green function, which is an harmonic function on the whole space outside the origin. And why is an harmonic function useful? Well, it's useful because using our harmonic functions, you can build martingales. So it's a nice fact that if you start a walk from some point and run it until you hit the origin, then during the whole trajectory, you were on points that the function is harmonic. And this process, this random process that evaluates the function g at every step that you had taken is a martingale. And then you can use this optional stopping theorem to prove quantitative results about the walk. Here we have an example. I'm calculating here the probability of the following event. You start from some point x that is inside an annulus. This annulus has inner radius r, little r, and outer radius big R. And you are asking for the probability that you hit the outer boundary before hitting the inner boundary. So this is essentially the gambler's ruin problem, but now we are on more dimensions than just one, okay? And using this approach, optional stopping theorem and this harmonic function, we can prove this asymptotic behavior, which is nice, and we essentially will do something very similar when we are talking about simple random walks on the plane. Okay, and so these are the properties I wanted to highlight. And now just some other tools that are important here are the following. So if you ask yourself, where does a walk coming from far away intersect A? Essentially, what you want to understand is a quantity that's called the capacity of a set. And this is the explicit definition. You are simply summing over all points of A the probability of course, if you want this probability to be 0, so the probability of leaving and never returning, okay? This is what I'm talking about. Of course, if you are inside set A, this probability is 0, so you only have to consider here points on the boundary of A, but this is not important. And so we have this quantity. Of course, we are considering finite A's here. So this is a finite quantity. And this is useful because it is in the definition of what we call the harmonic measure. You can define that harmonic measure in two ways. One way is simply normalizing the probability of leaving set A by the capacity. But another definition, which is the one that we care about, is that essentially when you are far away from your set, the probability of hitting set A at exactly point X, when you make Y tend to infinity, it will converge precisely to this measure, this harmonic measure. So essentially, you can see that the harmonic measure is, well, is what I described here. It's like you understand it as an entrance measure from a point that is coming from infinity and intersecting set A, okay? And why I'm introducing this notion? Essentially, because we are going to do the following. So we know that the uniform measure is the stationary measure. So suppose we start from a point that is far away from our set A. So far away here, I'm meaning just to be explicit, I'm taking some set of diameter square root of n that is surrounding A, and you're taking your point outside this set A prime. And you ask if you intersect the set A or not. If starting from X, you intersect it or not. If you are working not on the torus, but on the whole space, then, well, you know that the walk is transient. So if you start too far away, essentially the probability that you hit the set will be very small. So this is what this expression is saying. And we can do a similar argument to prove that the probability of when you are not on the whole space, but on the torus, and you start far away from A, the probability that you hit set A before the regeneration time will be small. And so what this means is essentially the following. If you start from far away, you regenerate before hitting A, okay? And then essentially you forget your initial conditions. So essentially what you get is that independently of which point you started, if it was from Y or Y prime, you get a uniform bound for the probability of hitting your set A at X. And this will be essentially given, this probability will be essentially the harmonic measure of A at site X. And this limiting procedure can be used to decompose our walk into excursions. So what do I mean by that? Suppose we start from some point far away and we run the walk. So we know that eventually you will hit set A because we are on a finite set. And then whenever you hit set A, you record this time, which we're calling R1, and start keeping track of the walk, okay? So here you did this nice trace until suddenly you got far away from the set A again. And now that you are far away, once again, you will regenerate before hitting A again. So you kind of forget your initial the states that you were, and you will hit set A at a second point at time R2 and repeat. And you keep repeating that until you get to time UN squared, which is for how long we are keeping track of the walk. And this construction is nice because instead of considering the whole trajectory of the random walk, now we have broken it into smaller parts and independent parts. This would be a first trajectory. This would be a second excursion, I'm calling them, okay? And then we can decompose the trace of the walk inside set A using these trajectories, these excursions. A final step is that you have to know how many of these excursions will happen. And this can be done. There are some arguments involving reversibility of the walk and also a little bit of renewal theory. And you can prove that essentially the mean time between excursions is given by the inverse of the capacity. And then we can estimate actually precisely asymptotically that the number of excursions during our walk will be given by this quantity, some multiple of the capacity of it. And finally, all of this is culminates in the following. We have a description of the trace that is the following. You can describe the trace of the walk at set A by first considering a Poisson random variable with this mean, which is just the one that we've just seen, the mean number of excursions. And then for each excursion will be independent of one another, and it starts from a point at the boundary, which is chosen independently using harmonic measure. And then you can run a simple random walk from there and watch what is the trace of the walk obtained by this random walk. So finally, when you are thinking of the torus, what you'd like to say is that the final trace of the walk is simply the union of all these traces that we are getting here, okay? And finally, when we are making n tend to infinity, it's interesting that we can actually define a model in the whole space that gives the trace of set A. And this can be done using a more formal description using Poisson point process. But here, this Poisson point process will be on a kind of a weird space, the space of doubly infinite trajectories. And here is just some intensity parameter. Essentially, what you get on this random interlacements model that would be the limiting model when you make n tend to infinity is a collection of infinite trajectories. So they must tend to infinity in both ends. And what the model is essentially a soup of these trajectories, okay? And then what you want to understand is the trace on set A of of this soup of trajectories, and there is a nice characterization of the process that is given by this exact computation here. So what this is saying is that the probability that for a fixed set A, it is not touched by any of the trajectories is given by the exponential of minus u times the capacity of A. Okay? And it's nice also to notice that why do you want to define such model on the whole space? Well, sometimes there is an interesting interplay between this discrete and continuous. I mean, for instance, we started talking about the problem about the torus and disconnection, and now we are talking about some model that has infinite trajectories and is defined on the whole space. So some results that you can prove for the torus can be translated about results for this model defined on the whole space. And in the same way, some results about random interlacements can be translated into results about the trace of the walk on a torus. So, and finally, all this construction that I just mentioned about random interlacements can be done also in a more general setting in which we consider instead of ZD any weighted transient graph. So weighted, I mean that you have some conductances on each edge of the graph, and the probability of choosing some edge is given by the mean, essentially a normalization. So you pick the probability of choosing this edge will be the conductance of this edge over the sum of conductances of all the other ones. Okay, I chose a very bad choice of color, but okay, just let's move on. And just to emphasize, you can prove this for any transient weighted graph. And just a little catch here is that you have to consider the capacity here for related to that walk, okay? So you are doing a simple random walk on a weighted transient graph. You have an associated notional capacity there, but the same formula holds in this context. And here I was talking a little bit more about this connection between results on random interlacements and results on the torus. For instance, you can ask yourself if the vacant set on random interlacements, if it percolates or not. So essentially what you get here is that you have a parameter u that controls the intensity of trajectories, right? So essentially when u is very small, you have very few trajectories. So the vacant set will percolate. And when you have u very large, you will have a lot of trajectories, and this will prevent any percolation at vacant set at level u, meaning that all its components will be finite. This has been proved in a series of papers, and it's nice that we have some similar results for the probability of disconnection on the torus, but I don't want to spend too much time on this because I said that half of the talk would be about this, and we haven't started yet the second part. So now let's talk about dimension 2. So essentially what I would like to do is a similar process, but on dimension 2. The problem with dimension 2 is that the simple random walk on the plane is recurrent. And why is this problematic? Well, if you consider a sub of excursions of random walk, well, each excursion will cover the whole plane, so the model is completely trivial. So you can't define in a straightforward manner But what can you do about this? Well, one solution will be to consider a walk that's conditioned on not hitting the origin. So let's define our model, and for that, I need to consider now the potential kernel. So the potential kernel is essentially what the green function was for dimension 3 and higher. It is this function. It has a maybe weird definition, but what's nice about this function is that it is harmonic outside the origin. And you can prove a lot of things about it. You can prove that, well, essentially that it is 0 on the origin is trivial. It is possible to prove that it is 1 at the neighbors of the origin. It is harmonic outside the origin. And we can also prove some asymptotic expression. So AX grows essentially as the logarithm of the modulus of X, of the norm of X, sorry. And then we have, essentially like the green function, we have an harmonic function that we can work with. And we use this harmonic function to define the following walk. So instead of considering random walk, we will define a walk at all the plane except for the origin. And the transitions will be given by, well, a quarter, which is the transitions of simple random walk, but we are weighting the transition according to the value of the potential kernel. So it is easy to check that this is indeed a walk, a Markov chain. It can be seen as a Doob H transform, but I don't want to spend time on this. But why do we define this walk? Well, it has nice properties. It has a very explicit stationary measure, which is given by the square of the potential kernel. It is also a random walk with conductances. And so for this walk, in principle, we could define the random interlacements if we had that this walk is transient, right? And indeed, if we compare these two walks.
Daniel, can I make a question? Actually, it's not mine. What happens if X is neighbor of 0?
Well, notice that y a of, so just let me draw a little. So notice that you start outside the origin, so you are never at the origin. If you are jumping to some neighbor, the probability will be given by the product of AY and AX, right? Over AX and times a quarter. And notice that you never jump to the origin because the value of the potential kernel at the origin is 0. Okay. Okay. So what is nice about this walk is that notice that when you are far away from the origin, we know that both quantities, A of X and A of X of a neighbor of X, will be essentially, when you make the ratio of their potential kernels, essentially 1, because you are, the behavior as X tends to infinity essentially as a constant times the logarithm of their norm, okay? So essentially, when you are far away from the origin, your behavior will be similar to simple random walk. Because essentially, this weight will be 1. But at the same time, suppose we have a path, x0, x1, xk, and we want to compute the weight of this path. Well, if you make this computation, you simply have to make this product And notice that there are a lot of cancellations here. So this one will cancel. And so essentially what you get in the end is that the probability of this path is the probability of a simple random walk path, but now it's weighted by this ratio. And now if x0 is, I don't know, maybe it's close to the origin, but if you are getting far away from the origin, you have a much heavier weight of this. This path has much more weight than simple random walk path. Okay? And this gives us hope that eventually this walk is transient. And this can be proved to be true. So essentially the same computation that I mentioned about dimension 3 and higher can be done for dimension 2 using that harmonic function that we have now, the potential kernel. So we can estimate the probability of hitting the boundary of some ball before hitting the origin for simple random walk. And what is nice is that there is a nice lemma that simply states that suppose you have some event that depends on what happens inside a ball of radius L, okay? And you want to consider the trajectories of this event. So if you look at this event considering a simple random walk conditioned that the walk hits the boundary of the ball before hitting the origin, this probability is essentially the same as the probability of our walk S hat, of our conditioned walk, being the same event. So essentially, this walk that we've just defined can be seen as a conditioned walk, a simple random walk conditioned on not hitting the origin. And so now I hope that the definition that we just seen seems a little bit less artificial. And what is nice about this conditioned walk is that using this computation about hitting the boundary of ball of an annulus, we can prove that indeed it is transient. Since we have a transient walk that is also defined on a weighted transient graph, the random interlacements construction of Teixeira works, and we are able to define a random interlacements model at 2 dimensions. So, as I said before, maybe you think that let me just, I'll talk about this later. So so here the notion of capacity for this walk is related to the notion of capacity that is classically defined for the simple random walk, essentially the same. And so what I wanted to say is that maybe you are still thinking that this walk maybe is just too artificial. So, okay, we can use this walk to build a random interlacements process, but is it actually close to the behavior of simple random walk? And it has been proven that yes. So to understand this, we have to mention some results that this was an open problem for a long time to understand the cover time of the simple random walk on a torus of dimension 2. There is an important paper of Dembo, Paris, Rosen, and Zeitouni in which they prove that this cover time is asymptotically essentially a constant time times n squared log of n squared. And it is a result of Comets, Popov and Vachkovskaia that essentially the walk that we just defined represents well what you expect to see of a simple random walk that does not touch the origin. So since I'm running out of time, I guess, I have to when? Sorry?
15 minutes.
15 minutes.
10, 15 minutes, yeah, if you have.
Okay. Yeah. So I should save some time for questions. So I guess I'll just skip this, and maybe if someone's interested, I can say more in the questions. So, okay, so I just defined random interlacements for 2 dimensions and its related random walk. But apart from this relation, it turns out that the random walk that we just defined, this conditioned walk, has some very interesting properties. For instance, there are some explicit computations for the time, the probability that the walk returns to some site that is given with using the potential kernel. And you can prove using these explicit computations that essentially, if you start from some point and look at the probability of hitting some point far away, it will converge to a half. So essentially, you are tending, this walk is transient, so it's tending to infinity, but it must spend some time at every scale, meaning any point has a probability of being hit that is very high. I mean, it's a half. And we are going to see some nicer properties. Just mentioning some, there is a green function for this, explicit green function for this walk too, but I don't want to talk about this. So for instance, using the property that this limit probability tends to a half, you can prove that every infinite set is recurrent for this walk. What do I mean by that? You take any infinite set you want, infinite, so, and the walk will hit it infinitely many times. Okay. What else can we say? So there is some property of bounded harmonic functions. This one is very nice. So suppose you have some set A, and you start doing some scalings of the set. So this will be A, this will be 2A, and so on. And you want to understand what is the fraction of sites that the walk visited. So essentially what you can prove is that the fraction of sites that the walk visited is converging to a uniform random variable on 0, 1. And also that although it visits a lot of sites, we also have some very large gaps, meaning that a similar construction, if you consider some set that does not surround the origin, because if it surrounds, then there's no hope that you can escape this set. But if it does not escape the set, then with probability 1, you will avoid infinitely many of these scalings of the set. So, and now to finish the presentation, I would like to talk about my work finally. And what we did was to investigate further how erratic this random walk is. Consider the following quantity, which we call the future minimum of the walk. So you can see this quantity as the following. So here we have a graph of the walk, essentially its norm through the time. And since we know that the walk is transient, you expect to see some wiggly line that is tending to infinity. And we define what we call the minimum, the future minimum. What is this? So if you take some time n, you will consider the whole trajectory from here on and verify which was the lowest point that you got. And of course, this must go to infinity. And what we do is to quantify how fast it goes to infinity. So here is the statement of how fast we can bound this minimum. So let me do a second drawing here. So essentially we have 4 functions. We have an uppermost function, which is essentially square root of n log 2, I guess, of n. And some function here, it's log of 1 minus delta n. This is tending to infinity, but it is lower than any power of n, okay? And eventually, our function will stay inside this region. So it can leave a little bit, but at some point it will be always inside this region. However, we also prove that it is quite erratic in the meaning that we have some other functions here, which are given by some power of n. And here we have essentially square root of n over some logarithm. And although we are eventually inside this blue region, the minimum keeps oscillating between these two other functions, intermediate functions. So this is what we can say about the speed of transients. And another question that we address in this work is about infinitely many encounters, meaning that, well, this is a classical question for simple random walk. If you start 2 independent simple random walks, you can ask whether they will meet infinitely often or not. Okay. For dimension 2, we know that this is indeed true. But what about our conditioned walk? And indeed, we can prove that it also has this property. And these were the results that we proved on our work. And now let's talk a little bit about the tools that we developed to deal with these 2 problems. So a nice property is that essentially when you are far away from the origin, we've seen that simple random walk is close to this conditioned walk. So we prove a tail estimate that says essentially that the norm of the conditioned walk cannot be too far away from the square root of n, which is what you expect for simple random walk. Also, we prove a version of local central limits theorem, which is a more quantitative statement about the probability of being at some site y starting from x. And finally, let's just say a little bit about the ideas that we use. The whole paper, we use a lot of Borel-Cantelli lemmas for all kinds of tastes. We have the eventually almost surely properties. They are kind of simpler. We can use that versions of Borel-Cantelli that simply if some is convergent, then the probability of the event that some of their probabilities is converging, the probability of this event happening infinitely often is 0. So these 2 events, they fall into this category. But for the other properties, we have to be a little bit more careful because we have to control their dependencies. And if you want, I can say a little bit more about that. But notice that, just to emphasize a little bit more of this, recall that the future minimum is defined using the whole trajectory from n onwards. So if you have two values, n1 and n2 here, these cannot be independent, right? And so we have to control the dependence of these events. Okay. And finally, for counting for the infinitely many intersections, we use a nice alternative proof of this result for simple random walk. Instead of doing the more classical computation that simply expresses explicitly the probability of returning to the origin, you can use the following quantity. You define some sequence of times growing very fast, and consider how many during this interval bk plus 1, how many times the walks meet. And you use a second moment argument to prove that this choice of scales is good, because we can see that the probability of having at least one encounter will be essentially bounded by a constant. Okay. And we can also control the second moment. And so using the Paley-Zygmunt inequality, we can, and also another Baroque-Cantelli lemma, this one a conditional version, we can prove that, yeah, actually in the paper, we do this proof both for simple random walk, just to be more didactic, I mean. And then we do a more detailed proof for the conditioned walk that also holds. And I guess that's all I wanted to say. So now I will open for questions.
Anyone has questions? You can open your microphone or write in the chat.
I have a question. Daniel, what's the difference between a local central limit theorem and a standard central limit theorem?
Well, it's just that central limits theorem, well, I know you know what it is. It's just some control. Well, you have a simple random walk, so you can understand it as sum of independent random variables, and you have some normalization that if you, well, they have, in simple random walk, they have mean 0, so you just have to divide by square root of n, and you will get a normal random variable. This would be the central limit theorem. The local central limit theorem, it gives more precise description of the position of the walk. So it gives, well, we saw, suppose that you want to understand this quantity. You start in at some site x, and for a large time n, you want to know the probability that you are at a site y. So you have some asymptotic expression that fortunately, I'm not recalling it exactly from the top of my mind now, but you have some asymptotic expression that gives you the probability of being at y after n steps when n tends to infinity. Okay?
Okay.
So, and just for our walk, expression, just lost it. So for instance, the central limit, local central limit theorem that we prove gives this expression. So you see it's not quite so explicitly as the one that you can prove for simple random walk, but still you can give some quite reasonable estimates for the probability of being at the site Y after n steps if you start from X.
Okay. In studying the future minimum is useful in this,
Well,
or I mean, because of the oscillations, you have a kind of, well, when someone show me a picture of oscillations, I think about the central limit theorem, and I don't know, it's useful here or it's not related?
Well, actually, the local central limit theorem is very useful simply because, well, in all of these results that I just proved, what we do is something like you start from some point, and after some not very long time, the walk is transient. So you will be around square root of n. And then you can compare the walk with a simple random walk because you are far away from the origin, so it's closer to being a simple random walk. So, and having these explicit expressions for the probability of the walk being exactly at site Y is very useful for computing many things here, and in particular for evaluating this minimum, the future minimum.
Oh, nice. Thanks.
Okay. Question. So, about the scaling limits of this walk.
Sorry, I can't hear you.
No, yeah, the question is, do you have any result or expectation of a result for the scaling limit of this special one?
I think we are not able to listen to you or listen up. Maybe
sorry.
Right.
You can write the question, or I don't know. There's a lot of interference, and it is very low the volume.
Can you hear now?
Yeah, now it's better.
Okay, sorry. Yeah, I was using the stupid earphones. Okay, so the question is about the scaling limits of this walk.
Scaling limits of this walk.
Yeah. I mean, the simple random walk is Brownian motion, and what should we have for this one? It's a two-dimensional Brownian motion, which is transient, perhaps. I don't know.
I actually don't know. I really don't know.
Oh, okay.
Maybe it's an interesting question.
Oh, okay. And so can I have another one? I mean, it's a quick one. I mean, you could think perhaps of other possibilities for trying to get a sort of simple random walk, which is transient, perturbing the usual random walk in a different way. I mean, is there anything in this direction, or
well, we haven't tried any other option. I mean, this approach using Doob transforms, they are, well, if you have some finite set and a harmonic function outside it, you can define a Doob transform for this function and define a walk using this. But I'm not sure if we have something interesting using this approach, or if everything is superseded by this condition walk, this walk condition to not hitting the origin. And anyway, a nice justification for choosing this is the one that the result of Popov and Marina at here it is, the one that I mentioned, that if you consider a simple random walk and look at the probability of some set not being touched by it, given that the origin is not touched by the walk, is in the limit, it will convert to the random walk, to the random interlacements model defined from this condition walk. But maybe there is some other condition walk that would be interesting. Sorry.
Maybe we are running out of time. If we don't have any other questions, let's thank Danielle. Stop the recording.
Okay. Thank you, everyone.
I will